In this video lesson, we're going to look at the classic problem in physics where you have an object sitting on a ramp. This problem can be one of the more difficult problems that you deal with in the forces unit. What makes it so difficult is not necessarily the math, but it's drawing the force diagram and understanding where all the forces go. So that's what we're going to look at in this video. We're going to look at how do you solve this problem by doing the force diagram and then calculating. So we're shown here that a block is on a ramp that has an angle of 25 degrees to the horizontal. The block slides down the incline at constant velocity. So immediately we know that this block is in equilibrium. Knowing that, let's go ahead and first start out with number one, which is drawing the force diagram. Now, let's do what we always do with force diagrams. Let's first start out by drawing our field forces, which is going to be gravity pointing straight down. All right. Now, what is actually touching the block itself? Well, the ramp is touching it, and so ramp is going to exert a force normal. Remember, force normals are always going to be perpendicular away from the surface. All right. And then finally, the block is sitting there going down this incline at constant velocity. So in other words, it must have a friction opposing it, otherwise it would be speeding up as it's going down. So since the block is sliding down, the friction is going to go up the ramp to oppose that motion. Now, when you have an object on a ramp, basically what you have to do is you have to imagine that your classic X and Y coordinate axis is being rotated or flipped, just like this. Okay, so you have to imagine that that's happening in your mind. Now, you don't need to draw that, but what you do need to understand is that when you have an object on a ramp, what we as physicists do is we imagine that the new x-axis is always along the plane of the ramp. So the x-axis is always along the plane of the ramp. If the ramp was this way, then the x-axis would be right here. Okay, so the x-axis is always going to go along the plane of the ramp. The y-axis is then going to be what's perpendicular to the ramp. That would be right here. So all we've done is we've just kind of oriented or rotated the coordinate axis in our heads. Remember, you don't have to draw this x and y, but I drew it just so you could see what's happening. So if you look, the only diagonal force that's there, technically speaking, is the force of gravity. So we're going to go ahead and split the gravity up. And the reason why we want to split gravity up versus the normal and the friction is because, think about it, gravity is doing two things in this problem. Gravity wants to pull the block down the ramp, but gravity is also what's responsible for pushing the block into the ramp. So gravity is doing two jobs here, and so since it's doing two jobs, we need to show that with the vector diagram split up. So let's go ahead and do that. Now, when you split up gravity in these cases, in these ramp problems, draw the gravity y first. So what that means is I'm going to draw gravity y first along the y-axis. So there's force gravity y. And now I'm going to draw force gravity x. Be careful when you draw force gravity x. Force gravity x does not just go across like that. If it did, then what that means is this would be the right angle, and then gravity y would be the hypotenuse. And that's incorrect. You don't want to do that. Instead, let me redo and go back a little bit. Instead, what we want to do is you want to draw the x component of gravity parallel to the x-axis, which is right here. So since the x-axis is tilted, so is my force gravity x right there. Notice how force gravity x is parallel to the actual ramp. So that means my right angle is now here, and force gravity is the hypotenuse of this triangle, which that's correct. Finally, what we want to do is we want to figure out where does the angle of 25 degrees go in our force diagram. The angle of 25 degrees is going to go right here. And here's how you know it goes in that corner. When I drew my force gravity going down, just like this. When I drew it going down, what I did is I created a right triangle right here. And so this right triangle right here, if this is 25 degrees in this corner, then this corner must be what? It must be 65 degrees. Okay, that makes sense. Now, when I drew the gravity y, which was right here, I made another right triangle. I made a right triangle that looks like this. And in that case, the right triangle, right angle, is right here. Well, if you know that this part is 65 degrees, then this part must be 25 to complete the right angle. So we were able to prove using geometry that if this angle is 25, this angle is 25. And remember, you don't have to prove that. You already know that that's true since I showed you once. So we can always now trust that that is correct. Okay, so now we have our force diagram that is drawn correctly. Let's review. I've got my force gravity right here, and it's been split into its x and y components. My force normal that goes off perpendicular, and then my force friction, which is parallel to the surface. Like I said, this is the hardest part of this problem. Now that we've got the correct force diagram, let's look at what's happening here. The sum of the forces in the x direction is going to be the force gravity x plus the force of friction. And since it's sliding down at a constant velocity, it is equal to 0. The sum of the forces in the y direction is equal to force gravity y plus force normal, and that's also equal to 0. It's an equilibrium in both the x and the y direction. Now that we have that, we can now do step 2, 3, and 4, hopefully with relative ease. Okay, number 2 says calculate force normal. Well, notice force normal and force gravity y together will be 0. So in other words, that tells me that force gravity y is just the opposite direction of force normal. So if I can figure out what force gravity y is, which is right here, then I can figure out what force normal is. Okay, I'm told that this block is 5 kilograms. So that means my force gravity, not the y or x component, but force gravity itself, or the hypotenuse, is 50 newtons. Now, if I know that this angle is 25 degrees, my hypotenuse is 50 newtons, and I want to solve for the force gravity y, which is the adjacent, what I'm going to do is I'm going to do cosine of 25 degrees equals the adjacent, which is force gravity y, over the hypotenuse, which is 50 newtons. That gets rearranged to be 50 times cosine 25 equals force gravity y. And remember, force gravity y is the same thing as force normal. So by calculating, and make sure you're in degrees on your calculator, not radians, I do 50 times cosine of 25, and my force normal is 45.3 newtons. All right, let's look at friction. Friction is going to be the opposite of force gravity x, as per the equation we wrote up here, since it's also in equilibrium. So in other words, if I can figure out what my force gravity in the x direction is, that's going to be the same as my force friction. All right, so let's do that. I'm going to use my triangle again. I know my angle is 25 degrees, and my hypotenuse is still 50 newtons. But now I'm trying to figure out what force gravity x is, which is the opposite. So the opposite in the hypotenuse, I'm going to use sine of 25 degrees equals the opposite, which is force gravity x, over the hypotenuse, which is 50 newtons. If I rewrite that, I end up getting 50 times sine of 25 equals the force gravity x. And remember, that's the same thing as force friction. Plugging into the calculator, 50 times sine of 25 gives me a force friction of 21.1 newtons. Finally, number 4 asks me to calculate the coefficient of friction. The coefficient of friction is going to equal my force friction over my force normal. My force friction is 21.1 newtons. My force normal is 45.3 newtons. And by dividing those two, I end up getting approximately 0.466 as my coefficient of friction. Notice that it's unitless because the coefficient of friction is a unitless value. The question then asks, is the mu or friction kinetic or static, and explain. The answer would be it's kinetic, And the reason I know that is because up here it tells me it's moving at constant velocity. If it was motionless, it would be static. But since it's constant velocity or moving, it's going to be kinetic. This concludes the video on the ramp problem for Unit 4.